Something. How about now?
Yeah.
Okay. So I just asked for questions. If there's any online questions, fire them up. And we're going to continue where we started off last time. There's a handout that I gave you over 2 lectures ago on acceleration of fluid masses. And what we've developed from all of this now is a general case of we have these finite fluid volumes with acceleration fields in addition to gravity. One, we see that if we have horizontal acceleration, we will have a change in pressure when we move horizontally. Again, think of some finite fluid volume. So here we have these little fish in a tank, and when you move to one direction, just like the glass of beer sliding down the bar, you see that with the horizontal acceleration, you're deflecting the free surface now. And so now if you think of moving horizontally from the free surface into the fluid, you're moving in a direction of increasing pressure. Likewise, if there's vertical acceleration, what we see is effectively what that vertical acceleration does is change the previous pressure distribution we had, and that was for fluid statics, P is equal to gamma H. Now, basically, if there's upwards of acceleration, you're going to be increasing pressures over what normally you had. And if you're accelerating AZ in the negative Z direction, you actually decrease pressures compared to fluid statics. When we look at the total derivative of pressure, we can then combine how pressure changes in both horizontal and vertical directions. And then if we just integrated that previous line between any 2 points in a fluid, okay? So here's some system, it's being accelerated, and it's got components AZ and AX. And so this is our new free surface. And if we move from any point 1 to any point 2, we can look at integrating that third bullet, and that would then give us the fourth bullet, where the pressure difference between those 2 points from 1 to 2 is a function of movement in the horizontal direction, movement in the vertical direction, as well as the acceleration fields in both horizontal and vertical direction. In that fourth line, where we did the integration, again, if there is no horizontal acceleration, there's no pressure change in the horizontal. And what you would see in that fourth line is if AX goes to 0, then that entire term goes to 0. And then what we did was look at that fourth line and look along a contour of constant pressure, which means P1 is equal to P2, for example, just riding along the free surface. When we look at a contour of constant pressure and then solve that fourth bullet for dz dx, that's the slope of that contour, slope of the surface, but it's also the slope of any contour of constant pressure. And that slope or the contour of constant pressure is related to both horizontal and vertical accelerations, as well as, of course, gravity. So that's just a wrap up of what we've been doing the last class and a half. Last time we did an example of just vertical acceleration. Next example, we're going to look at horizontal acceleration, then we'll look at both. So, for example, what horizontal acceleration is necessary to incline a water surface at 10 degrees off of the horizontal? Okay, so in this case, we're trying to figure out what is the AX necessary to create this system. The original system would have had this horizontal water surface. The new system is this sloped fluid surface. Okay, so in this case, we're saying it's a water surface. So again, just going to the previous slide, all we have to do is find out the horizontal acceleration, which is going to give us an inclination of 10 degrees. That 10 degrees is dz dx. It's the tangent of that angle. Okay, so we employed that equation. So again, if you think of the geometry, if this is theta, this is dz, and that's dx. And what we're saying is, we know theta is 10 degrees. It's actually a minus 10 degrees because we have ax in the positive x direction. So in this case, we're trying to solve for this. There is no az. We're asking, what is the horizontal acceleration necessary to create this condition? And so we know what theta is, and therefore tan theta is dz dx. And therefore, there's only one unknown in this equation, ax. We know the acceleration due to gravity. So again, when we have ax positive, our coordinate axis system is always z positive upwards, x positive to the right. So when we say we're inclining at 10 degrees, we're actually looking, when we have a positive ax, we have a negative 10 degrees. Or we have this slope, this dz dx slope is actually a negative slope in this zx domain. So in this case, ax is solving the equation, the first bullet for ax. Ax is equal to g plus az tan theta. And again, that negative sign does not appear below because we're saying we have a negative slope. It's already built it. We're building it in on that. So in this case, since az is 0, ax is g tangent of theta, 9.81 meters per second squared times tangent of 10 degrees is 1.73 meters per second squared. So you have this tank of water. Did I give you the dimensions of the tank? It doesn't matter. It doesn't matter if it's a tank the size of this room or just a little cup of coffee. You accelerate to the right, you're going to get this slope. That equation on the first bullet of this slide has no dimensions in it. Physical dimensions of length, width, height. It's whatever that finite volume is. You accelerated at 1.73 meters per second in the positive x direction, you're going to get a slope of 10 degrees for that fluid volume. And every contour of constant pressure is at a slope of 10 degrees as you move through that fluid. So you can, and we'll go through this in the next example, calculating the pressures and then forces at different locations. So any questions on how we did this? In the second slide of today, I gave you a summary of all the equations. Whenever you have a problem where it's giving you an acceleration other than gravity, these are the equations that are applicable. And they're either asking for what's the acceleration, what's the net geometry, what's the pressure, what's the force, but it's all the same equations. It's just you're trying to isolate the variable of interest in those problems. So I said that we had a container of water. What if the container was filled with mercury? Does the answer change? Go back to that equation and what we were asking for. What is the horizontal acceleration necessary to incline now a mercury surface to 10 degrees off the horizontal? That's the equation we used. Where are the fluid characteristics of mercury in that equation? Nowhere. So you will get this irrespective of the fluid. What will happen though is in the unsteady state, for example, when you first start with it static and you initially start the acceleration, for that fluid surface to actually go from 0 to 10 degrees, that's where you'll see the difference. Water may do it much faster than mercury because of viscosity. But the steady state system is in this equation and has nothing to do with what the fluid is that you're using. It has everything to do with just the acceleration fields. So I want to talk about this first, then we're going to do a numerical example. how would you find the pressure distributions? So this was our system. Again, this is the final state, and that was the initial state. So it was at rest, horizontal surface. Accelerate to the right at 1.73 meters per second squared, and you get a fluid surface of 10 degrees off of the horizontal. Note the symmetry. It went up on the left-hand side the same distance it went down. Now that's true if you have a symmetric container. If it's not a symmetric container, that wouldn't be true. Okay, but if you consider this like a box or a rectangular structure, it would go up the same on one side as the other. If it was a cylinder, it would do the same thing. So if you wanted to know the pressures throughout the system, this is the pressure equation we developed. The change in pressure going from one point to another is affected by movement in the x direction and movement in the z direction. So this is the equation that we generated by putting the two partial derivative statements for x and y pressure changes. So we could look at 4 points, for example, in this system. Point 1 is the upper left-hand side. Point 2 is directly below it on the left-hand side. Point 3 is the bottom of the right-hand side, and point 4 is on the right-hand side upper. We have a free surface. So we had this container, we accelerated. What can you tell me about P1? It's atmospheric, right? 0. How about P3? 0. So we're going to use that to our advantage. And again, note the symmetry. It goes up on the left-hand side the same amount that it goes down on the right-hand side. So before we get into the mathematics, two fundamental different systems using the same set of equations. One is what they make laws about, open containers, right? You're driving with open containers. The other is if you have a closed container. The difference is in an open container, if you accelerate it fast enough, you can actually start to lose volume. And that creates a problem when you're trying to calculate pressure distributions and forces. Okay? So I think you understand that if you accelerate an open container high enough, you start to spill fluid out the top. The equations we developed are still relevant. They do not lose, do not modify them at all. And so again, the equation we just used for the slope of the surface is still relevant whether or not you lost fluid. You're still going to have that slope to the surface. And that is what helps you to identify whether or not you lost fluid, as well as how much fluid you lost and how much fluid is remaining. This is defining the system geometry. That fluid surface slope, dz dx is equal to minus ax over g plus az, defines geometry from which you can determine everything. So again, before we have any acceleration, we have some initial volume. Length times width times height, if it's a rectangular system. After we have acceleration, this is what our system looks like. And of course, if we're accelerating the other way, it's just going to be a mirror image. If we have z component of acceleration, it will affect this slope. So I'm just trying to simplify right now. The real issue is when you have that acceleration, you want to figure out, did the fluid surface go over that opposite side? If it did not, you haven't lost the volume and you have no overtopping, and your original volume is your final volume. If you calculate from this slope that it must go at least to that point, it can never go above that point. If it goes above that point, you've lost fluid. And so this point then becomes a fixed location from which the tangent of theta or the slope occurs. So you could actually keep increasing AX, and now you've lost fluid, and you can keep increasing AX such that you're losing more fluid, and now the slope is actually riding along the bottom. But this slope is all dictated by dz dx. So once you have the accelerations, it dictates what this ultimate slope looks like, and it dictates whether or not you lost fluid volume. That is true for open containers. Again, you could have possible overtopping with excessive horizontal acceleration. Everything I just drew in there. Again, I'm just indicating that that slope dictates all the geometry. When you've lost fluid, you don't know if you have the same fluid volume anymore. In a closed container, by the name closed, you're not losing fluid. Okay, and so what happens is the pressure distributions are changing, and now dz dx is identifying the contours of constant pressure, but you haven't lost any fluid. So this equation is describing the contours of constant pressure in practical situations. For example, these systems are vented somehow. So you may not lose fluid, but somehow, you're not creating these pressure vessels where you have excessively high or low pressures. So typically you do know some information somewhere. So in the closed containers, again, the big difference is you will not spill anything. Initial volume is preserved. And again, very often our real engineered systems are very often vented to the atmosphere. And so what we would have again is this equation is operable, and all that equation is describing is the slope of the contours of constant pressure. You can always go from one point to another point. And at point 1, we have P1. At point 2, we have P2. And I'll show you the equation again, but we've already integrated the equation to figure out the pressure difference from one point to another. To solve that equation, you would either need to know one, or all you're after is the pressure difference. And again, I'm going to be doing an example where I talk about this. So here's that example. Here we have an open container. It's half filled with oil, and the specific gravity of the oil is 0.85. It's accelerated to the right, and that acceleration vector is 10 degrees off of the horizontal. So here's our acceleration vector, and it's 10 degrees off the horizontal. And that acceleration vector is 5 foot per second squared. And so you'll see the container on the next page, but it looks something like this. It's a nice rectangular container. And so if we are accelerating to the if we're accelerating at 5 foot per second squared at this angle 10 degrees off the horizontal, we would expect the fluid surface to do something like this. And what we're asking is, what's the pressure distribution on the left-hand side? And what's the pressure distribution on the right-hand side? And they will be linear pressure distributions. Okay. Once we know the pressure distributions, we can then calculate the force on the left-hand side, and we can calculate the force on the right-hand side. So that's what we're after in this problem. So here's our container. And so again, going back to the problem statement, the open container is half filled with oil. Okay, so you see that this volume is half the distance of each side. And the dimensions of the container is 5 feet high by 20 feet in length. And it's got a width of 10 feet. So that's our container that we're moving down the road. And we're having this acceleration of 5 foot per second upwards and to the right. So that's our initial condition. And obviously, if the system is half filled and you have 5 foot of height of one side, then this distance is of course 2.5 feet, right? It's half filled. And it's oil. So after we accelerate, this is what we would expect. We would expect that that acceleration of 5 foot per second squared at 10 degrees off the horizontal is giving us a system that looks like this. And when we have the system that looks like that, again, we need to identify whether or not we spilled oil. You cannot calculate the pressures on either end and therefore the forces unless you know that you have not lost volume or you have lost volume. That geometry will work its way into the pressures on each side. So just for example, what if you accelerated it high enough that this was your final condition? What's the pressure distribution over here? Atmospheric, right? There's no fluid on it. So that you have to figure out whether or not, when you have an open container, whether or not you've lost fluid. So we don't know if this acceleration field forced us to lose fluid or not. However, we know that the geometry with the acceleration field is going to dictate the slope of that fluid surface. Theta is the angle off of the horizontal due to the acceleration fields AX and AZ. So what we'd like to do is calculate tan theta and then figure out if the fluid surface exceeded that left-hand side pinnacle at 5 feet, if the deflection was 2.5 feet on one side and 2.5 feet on the other. So the horizontal acceleration, again, you've got an acceleration that can be broken into components, AX and AZ. AX, the horizontal component, is 5 foot per second cosine tangent 10 degrees. And AZ would be the 5 foot per second squared sine of 10 degrees. So we have the two vector components of our acceleration field of 5 foot per second squared broken into X and Z components. And now we can calculate what the tangent of theta would be, that is the slope to the surface. So again, knowing AX and AZ, we can calculate the dz dx is minus 0.149 feet. What does that mean? Again, we have this container that's 20 foot in length. And dz dx equal to minus 0.149 feet means that if you go horizontally 1 foot, vertically, you have lost 0.149 feet, right? dz dx. So theta is minus 8.47 degrees, meaning from the horizontal, our surface is 8.47 degrees below the horizontal when we look at it this way. Okay. It's not so bad. So now we're trying to answer the question, did we spill any fluid? Well, to figure out if we spilled fluid, what we would like to do is calculate that height. We know that the height of one side is 5 feet. And if this was initially half full, that's 2.5 feet, which means this distance is 2.5 feet, right? And so if we calculate that distance on the left-hand side h, if it's 2.5 feet or greater, we've spilled oil, right? And so when you make this calculation using the geometry of the system, you know you cannot have the fluid sitting at the left-hand side above the end. That can't happen. That's why if you calculate h to be greater than 2.5 feet, What you really have is this. The fluid goes right to that left-hand side and it just keeps spilling there until it reaches an equilibrium volume. Okay, but you still know the geometry. So we'd be after calculating H, and what you have is a very simple right triangle. You have a 20-foot base, and because of the symmetry, you have a triangle that is 10 feet by H, right triangle, with that angle of 8.47 degrees. Right? So in this case, H is equal to L over 2 tan theta, where L is the 20-foot distance. Or H over L over 2 is the tangent of theta. And so we can put in what we know for L and theta, and that tells us that H is 1.49 feet. And again, if it goes up 1.49 feet on one side, it went down by 1.49 feet on the other side. So that 1.49 feet is less than 2.5 feet. That means you have not spilled fluid. And again, if this, and you'll see this on the next slide, if this is 1.49 feet and this is 2.5 feet, then the total distance on the left-hand side is 3.99 feet. And on the right-hand side, you'd have 2.5 feet minus the 1.49 feet, or 1.01 feet on the right-hand side. So we know the geometry. It's all right triangles. So this is that system I just drew for you. We know we didn't spill any fluid, and so the fluid is not going to the very top. We know it went up 1.49 feet on the left-hand side, went down 1.49 feet on the right-hand side, and so we have a geometry where we have 3.99 feet of oil on the left-hand side and 1.01 feet of oil on the right-hand side. So the first question that was posed was, what is the pressure distribution on the left-hand side and the right-hand side? Now we can answer it, now that we know we have not lost fluid. Again, with open containers, you can't get to that question until you know whether or not you've lost fluid. So we can go from point 1 to point 2. Point 1, we know what the pressure is. It's a free surface. And we can calculate the pressure at point 2. We could move over to the right-hand side. We know the pressure at point 3. Again, it's still a free surface, even though it's sloped. And we could calculate 4. So before, with fluid statics and manometers, we could go from the free surface, for example, to any other point. And we could calculate the pressure at point 2 if we knew the pressure at point 1. And basically, that's what we're going to use the new set of equations we have that include accelerations. We're going to start at one point and go to another and use the fact that we have a boundary condition, that we know what the pressure is at some specific location. And what you're going to see me do is, I'm going to go from 1 to 2. I can call this an origin. Right? And again, all that's going to do is when I integrate the equations, P1 is going to be 0, where X1 is 0, where Z1 is 0. If that is my origin, what are the coordinates of X2, Z2? Well, the left-hand side is a vertical wall. So what's X2? 0, right? Just going vertically downward, you're not changing X. Z2. And Z2, again, the oil is 3.99 feet deep on the left-hand side, and Z is positive upwards. So Z2 is minus 3.99 feet. So you're going to see these in the future diagrams, but it's really no different than what we did before with fluid statics. These coordinate systems are there, but we boiled it down to P is equal to gamma H. That implicitly occurred from a free surface where Z was 0 and pressure was 0. So we're going to compute the pressures at 1, 2, 3, and 4 to get forces on each end. Once we have pressures, we can get forces. So we already know, and I described in the last slide, P1 is equal to P3 is equal to 0. They're the free surface. For the left-hand side, we're going to start at point 1 and go vertically downwards to point 2. We let the origin for this analysis going from point 1 to point 2 on the left-hand side. We let the origin be right at the free surface. X1, Z1 is 0, 0. X1 is equal to X2 is 0 because you're going from point 1 to point 2 along a vertical line. There's no change in X. So this was one of the equations we started with on the second slide of today. It's one of the equations we derived. And the analogy to this was for fluid statics. Whoops. That was our analogy in fluid statics. dP dz is minus gamma. So here we have the change in pressure will occur due to any changes with movement in the x and any changes with movement in the z, as long as you have both ax and az. We take that equation for dp and we integrate it between p1 and p2, and we integrate it from x1 to x2 and from z1 to z2. And what you get is the second to the last bullet. The integral of dp is p, evaluated at point 1 and point 2. So that's p2 minus p1. The other integrals, what you'll see is I took those negative signs, and instead of x2 minus x1, I brought the negative sign inside and I get x1 minus x2. So that's where the negative signs went away. And then what we know is, again, when in doubt, cancel out. The pressure at the free surface at 1 is 0. X1 judiciously selected was the origin. X2 judiciously selected to be vertically below X1, 0. Z1, 0. Okay, and this is exactly what we did in fluid statics. You just don't see all these zeros floating around. We just developed it into P is equal to gamma H. And that's basically what you see here. Whoops. So the last bullet just got rid of all those zeros, and P2 is the specific weight of the oil divided by acceleration due to gravity, the vertical acceleration AZ plus gravity times a minus Z2, and Z2 is a negative number. So you have a double negative there. Yeah.
You go over why X1 and X2 are both 0 again?
Sure. So this point on the upper left-hand side is X1, Z1, and this point is X2, Z2. Okay, it's a vertical line. And we're going to do the same thing when we go from 3 to 4. Could we have selected a point right here? Absolutely. You just need to know the X, Z, and pressure conditions at whatever other point you pick. But I typically am kind of showing you judicious selection of points to get rid of as many terms as you can. Okay, so this last equation on this slide is the first equation on the next slide. And specific weight of oil is specific gravity of oil times the specific weight of water. We were given that the specific gravity of the oil is 0.85. Specific weight of water is 62.4 pound per cubic foot, and that gives us specific weight of the oil of 53 pound per cubic foot. So putting everything we know into that first equation, this is the specific weight of oil over gravity, 53 pound per cubic foot over G. The next terms are the vertical acceleration plus gravity. We calculated AZ to be 0.87 foot per second squared, and gravity is 32.2 foot per second squared. The minus sign is right here. And then Z2, as we indicated, is a minus 3.99 feet. Z is equal to 0 at the free surface on the left-hand side. and Z2 is the minus 3.99 feet. So when you multiply that all together, you get P2 is 217 pounds per square foot. So if this is our container, our pressure distribution looks like this. It goes from 0 PSF pounds per square foot at the surface down to 217 pounds per square foot. It's a linearly changing pressure distribution. Look at this equation. Is gamma, is the specific weight changing as you move through the fluid? No. Is the acceleration due to gravity changing as you move through the fluid? No. Is AZ moving as you move through the fluid? No. Is G? No. The only thing that's changing as you move along that left side is Z. And that's why you have a linear pressure distribution. We want to convert that into a force on the left-hand side. And that's just going to be the pressure at the center of area times the area of the left-hand side. How would you calculate the pressure at the center of area? In a linearly changing pressure distribution. Pressure at the top plus pressure at the bottom divided by 2, right? So if I looked at the end, this is what the left-hand side looks like. And the fluid surface is 3.99 feet deep on the left-hand side. So you have this rectangle being submerged in a fluid. Above that 3.99 feet, it's in air. Pressure on it is 0. So finding the pressure at the center of area is just the average of the pressure at the top and the bottom. Okay. And then that area would be 3.99 feet times the width, which we said was 10 feet. That's not so bad, is it? So we'll calculate that on another slide. We're at the doorstep of calculating the last thing we were after. First, you were asked to calculate the pressure distributions on the left and the right, and then you were asked to calculate the force on each side. Okay, so we're going to go from the left-hand side to the right-hand side. And on the right-hand side, we've got 1.01 foot depth of oil. And we called point 3 and point 4, respectively, the fluid surface on the right-hand side, and point 4 was at the bottom of the fluid surface on the right-hand side. 4.3 we're going to say, I'm going to let that be my coordinate axis system 0. That's my origin. Okay. You can certainly use the same origin that you used before for point 1. You don't have to, but if you use the left-hand side upper corner as your origin, you need to now find the X and Z coordinates, X3 and Z3, with that being your origin. All you're doing is complicating your life. I'm telling you, when you're asking for questions about pressure distribution, you're going to have to integrate that equation that's here. You have to integrate that between 2 points. My suggestion to you, if you can make one of those 2 points on the free surface and your origin, you get rid of 2 terms right off the bat. You get rid of a pressure term and you get rid of a location term, say an X term or a Z term. So we're going to go from point 3 to point 4. We want to find the pressure distribution on the right-hand side. We already know the pressure at 3 is atmospheric, it's 0. We're going to set a new coordinate origin at the free surface on the right-hand side at point 3. So X3 and Z3 are 0. We're going to move vertically downwards from point 3 to point 4. So X3 and X4 are the same, because you're just moving vertically. So our general equation is dP is equal to minus gamma over G AX dx minus gamma over G AZ plus G. And again, we're integrating this from points 3 to 4. So P3 to P4, X3 to X4, Z3 to Z4. And that gives us the equation, which is the second to last bullet. P4 minus P3 is everything on the right-hand side. We know P3 is 0 because we selected point 3 at a free surface. We know X3 and X4 are both 0. X3 is at the coordinate origin, and point 4 is immediately directly below it, so there was no change in X. And then we know again, since point 3 is the origin, that term's equal to 0. And so we're left with this equation here that looks very similar to what we did on the left-hand side, only the difference was subscript 2 instead of 4. It's the same equation. The only difference in this equation from left to right is the Z term is different. On the left-hand side, it was minus 3.99 feet. On the right-hand side, it's minus 1.01 feet. So there's that last equation. And from this equation, this should be P4. I copied and pasted. So what we have is gamma over G. We already identified the specific weight of the oil is 53 pounds per cubic foot, divided by the acceleration due to gravity, times the sum of the vertical acceleration plus gravity, the 0.87 foot per second squared plus 32.2 foot per second squared. The minus sign, again, is right there. And Z4 is minus 1.01 feet because we go from 0.3 to 0.4. And on the right-hand side now, we go from P3 equal to 0 PSF to P4 is equal to 55.1 PSF. And what we can then do we can then take that linear pressure distribution, calculate the pressure at the center of area, and then with that pressure at the center of area, multiply it by the submerged area to get the force. So again, for the right-hand side, you've got something that is 10 feet into the board by 5 feet high. That's the full side of the tank. But you only have a depth of oil of 1.01 feet. So the center of area is right here, G. Okay, so that's the area we're talking about, 10 feet by 1.01 feet. And the center of that area is half of 1.01 feet, 0.505 feet from the top or the bottom. Okay, so I was creating this just before class, and I did something and I hit escape and I lost all my slides. So we're going by hand right now. So the force on the left-hand side, as we just identified, is the pressure at the center of area times the area of the left-hand side. And since we know these pressures, this is going to be equal to the pressure at the center of area on the left-hand side is the 0 PSF at the top plus the 217 pounds per square foot at the bottom over 2. That's the pressure at the center of area on the left-hand side. And the area of the left-hand side is 3.99 feet times 10 feet. That's the depth of oil on the left-hand side, and that's the width. 10 feet is the width. So that's equal to 4,330 pounds. I would actually like a commentary after today. Either tell the TAs or tell me if this is an acceptable way to go. In the future, I may do more of this and less of all these figures that you're rapidly trying to copy, because then I have to write at the same speed that you do. So if you can keep up with me this way, better than you can keep up with me with all those pre-made slides, let me know. We're after continual improvement here, and it will happen before December 10th.
They like this way better.
They like this way better? Everybody's a critic. So, that's the left-hand side. Now let's do the right-hand side. That comment came in way too quickly, and I also know that other people will say they don't like it. I always know I cannot please everybody. I'm just trying to please as many as I can. So I'll probably be doing mixtures for the rest of the semester. So same thing on the right-hand side. We need the pressure at the center of area times the area of the right-hand side. And similarly, we would get that by getting the average pressure on the right-hand side times the submerged plane area of the right-hand side. So this is equal to the pressure at the top, 0 PSF, that's 0.3, plus the pressure at the bottom, the 55.1 PSF, that's 0.4, over 2. And then the submerged area on the right-hand side is the 1.01 foot of depth times the 10 foot of width. And that gives us 278 pounds. All right, since you're so good at this now, let me ask a really foolish question. Where do those forces act? So let's look at the left-hand side. Here's the left-hand side, and here's the pressure distribution. What is the shape of that pressure distribution? What does it look like?
Triangle.
Triangle, very good. Where is the center of area of a triangle? 1/3 up from the base, right? Before, when we wanted to identify where forces on submerged surfaces acted, we used this equation, YCP, the distance along the inclined axis to the center of pressure. Remember that? When you use that equation and your surface starts at the surface, such that you have a triangular distribution, you will get YCP 1/3 up from the base of the triangle. Complete consistency. So you know where these forces act. If this is 3.99 feet, that's the total height. The distance here is 3.99 feet over 3. 1/3 up from the base.
I think the screen is frozen.
My screen is frozen or their screen is frozen?
Someone's is frozen. They're saying, oh, no, they said it's good now.
Okay.
It's good.
So you know where these forces act. Next foolish question I will ask. Is the left-hand side force equal to the right-hand side force? Are they the same? No. What does their difference equal? I'll help you a little bit. This is where it all started. We started with this differential cube. And instead of statics, where we said sum of forces equals 0, with acceleration fields, sum of forces is mass times acceleration. So if you actually go through this, what you would see is MAX is the density of oil times the original volume, which you know, 2.5 feet high by 20 feet long by 10 feet wide. You know the original volume. The density of the oil, we calculated the specific weight, just divide that by acceleration due to gravity, and then AX. And I will leave that up to you since I'm out of time, but what you get is 4, So I'm out of time. All I did for those of you, I can't remember, I don't know when it kicked out, but I just demonstrated that this is true. Go ahead and back up. I gave you a handout on continuity, and we're going to go very quickly. I'm not going to do the derivation. I'm going to go to the operative equations. So read that handout for next time. And I might give you a few problems for homework, but they won't be due till Monday. See you Friday.
I'll just show.
It's still going on. I need to stop the share.
We can't put bad things.